Hi, I want to tell you about, well, electrical current, charges moving, so this is pretty exciting. Whenever I hear the word current, I think of current on a river, and we can make all kinds of analogies to water. So let me just start out by saying a couple stupid things about water. If you have a tube of water and you lift up one side and lift up the other side at the same time, then water won't move. You'll have the same level, and yeah, it's all water in here, but it won't flow. But if you have a tube of water and you lift up one side and the other side is not high, then water is going to come out the low side because of the action of gravity. So this water will be going that direction. I think there are no surprises there. But it really shows us that, well, we can make a beautiful analogy to electricity. This would be a certain potential energy here and a certain potential energy there, and this is a high potential energy and this is a low potential energy. But you know, really we're not talking about potential energy so much, we're talking more about potential. And so we can start to think about voltage, and it's voltage that determines whether something will cause charges to move or not. And this would be both sides of a wire. Maybe I could say both sides of a circuit at same voltage. And this would be voltage difference. And so a voltage difference would cause a potential difference. Well, that's what it is, right? But it would cause a current, which would cause a charge to move. I'll just define current right here. Current is an I. That's interesting. It doesn't seem to make any sense, but boy, you really wouldn't want it to be a C, because there are two C's already. There's a C for capacitance and there's a C for coulombs, the charge itself. So current is how much charge goes through a certain area of the wire, just a delta Q, the charge going through a certain spot, divided by how long it takes. And yeah, you know that this is definitely a derivative. It's dq dt through some cross section of the wire. So I should give you a wire. Let's have a nice primrose wire here. And if I make a cross sectional area of the wire, then an esteemed physics teacher once told me, it's Mr. Wojak, he's still rocking, if the reason it's called I is because the eye of physics is, these are the eyelashes of the eye of physics. The eye of physics is counting how many charges make it through this area in some amount of time. You see, if I turn on an electric field in the wire, what? An electric field in the wire? Oh dear, we said previously that conductors couldn't have electric fields, right? I'm planning to turn on this electric field in this wire, and the charges will move. Do you remember which charges move? Is it the protons or the electrons? Yeah, it's the electrons. So the electrons all, well, let's see, I'm going to set up my electric field that direction. So the electrons want to go to whatever causing the electric field, and that means each of the electrons is going to feel a force this direction. And they're not going to go directly that direction because there are a whole bunch of things that will prevent the electrons from moving. Let me write that the velocity of the electrons is that direction. When there's an electric field, the opposite direction, because of the charge, right? So they feel a force to the left. And that's just the overall velocity of the electrons, because they're going to be bouncing around in a really random way and interacting with the gunk that the wire is made up of. So this implies sort of things like resistance and such, and we'll get to that very soon. But I guess I also want to tell you, let's see, we've got electric field and velocity electrons. The problem is Benjamin Franklin, okay America, good work. So Benjamin Franklin was a patriot and a scientist as well, and he was America's first physicist in my opinion. So he was doing a lot of experiments with electricity, and he decided that, well, positive charges moved because he couldn't do any experiments that taught him any better. And Isaac Newton approves. So Ben Franklin says positive charges move. And you know that negative charges going to the left in this wire is functionally equivalent, except if there's a magnetic field. This would cause this statement to be untrue. But if you're just looking at electrical effects, if you've got electrons going to the left is going to get more negative and the right is going to get more positive, right? That's the same thing as if protons were going to the right. Now, Benjamin Franklin screwed this up. Unfortunately, he couldn't do any better experiments, but the conventional currents direction is said to be parallel to the electric field, and therefore, consequently, and oh shucks, opposite the direction of the velocity of the electrons. That's going to be very annoying for you, but I'll just set up a little circuit. Let me see, I'll give you a battery. And there's going to be a resistor over here, and a resistor is choppy, so it's hard for electricity to get through it. This is the positive side of the battery, and that's the negative side of the battery. A lot of times, I'm just going to abbreviate batteries like that. So the large side is always the positive, and the negative is always the short side. But for the first time I draw it, I'll draw a nice big happy battery. Now, you know that electrons are moving, so they'll be coming out the negative side and going this direction, and going through the resistor right here, and going through and going back into the battery. And inside the battery live little fairies who like to pump electrons from this side to that side. They don't want to be over here, right? The electrons have higher energy here than they do right there. In fact, all the time the fairies are pumping the electrons over here to the negative side, exactly where they don't want to be, they're raising the potential energy of the electrons. And therefore, they're decreasing the actual potential here. So that's what this means. This is low potential, and this is high potential. Typical battery in the United States is 1.5 volts. That shows the difference in potential between the left side and the right side. And if you think about a charge, maybe a coulomb of charge moving in the battery, then you could think about the potential energy difference between the coulomb of charge being here versus being here. And that enables you to do some really cool calculations about the energy stored in a battery. It turns out that work in a circuit, or work in a battery, same kind of argument, is just how much charge you've moved times what I'm going to write just one time as the electromotive force. This squiggly little E right here is called EMF, and it is an extremely archaic and stupid name, and you'll see it in a lot of textbooks, and boy, I'd love somebody to try to defend it to me because I hate it. I don't think that this word should be used ever again. It comes from a time before truly the interaction between electricity and magnetism was understood, and it was thought that it was something special, but it is truly just electric potential. So I'm going to call this the voltage of the battery, or the voltage of the circuit. So work, oh, wait a second. This statement right here is exactly equivalent to the statement that change in potential energy is charge times voltage. And that's actually how we define voltage. Remember we said voltage is change in potential energy divided by charge? Sure, so this equation shouldn't come as any surprise, but in this case it's going to be useful to think of the work done by the circuit, by actually the electric field in the circuit, is how much charge you've moved times the potential of the battery. And what should we do next? Oh, I wanted to make an analogy to this circuit right here. There's electrons moving that direction. And the problem is the electrons are moving that direction. That's true and physical and real, but we say that current is moving the opposite direction. And some people call it conventional current. I'm just going to call it current. The direction of the current is clockwise because current comes out of the positive side and goes into the negative side. But it's not really a thing. I mean, what is current if not just the motion of the electrons the opposite way? Let me say that one more time. That's very annoying. Current is when electrons are going the other way. I guess there's one possibility that current could actually be in the proper direction as specified. If you've got some beaker of some goo and you hang out with chemists and there's some stuff in here, and this would be like the plus terminal and this would be the minus terminal. If you had positive ions in this soupy purple goo here, then the positive ions would go from positive to negative. And we could say they obey direction of current. But it's unfortunate that inside a wire, the current will always be the opposite direction of everything that is actually moving. Oh, how frustrating. But we're stuck with it, and there is no way out. I don't really want you to blame Benjamin Franklin because he did some great work. But my point is we can make an analogy between electrons being pumped around in here, or let's say pretend positive charges that move this direction. In fact, from now on, I intend to talk only about positive charges moving because they don't, but it's so much easier to think about it as if they did. The analogy here is the pump, this battery with fairies inside of it. This could be me, for instance, and I could be standing over here and lifting up a cup of water, and hopefully I could lift it up really quickly. So I've got this cup of water, and I've got this flurry of arms doing this really, really fast. I fill up a bucket of water and dump it into a ramp here. This ramp right here. Okay? So I'm going to fill up the bucket of water and dump it, and the water will go over here, and it will run down. It has high potential. And then it runs down into here, and it can do some work, right? Because it will be going fast when it gets to here, and so I could have a little wheel with little spiky things coming out of here. What do I mean to say? This is like a water wheel, I guess. So the water wheel will turn clockwise, and I will be doing work. Wow, I need to change my bucket a little bit. I will be doing work, and the water will come down here. So I want you to think of voltage. The way I can get from low voltage to high voltage is by doing work on the charges. And the way I do work on this water is just to lift it up. The way I do work on charges is I need a battery, or I guess I could have a capacitor or something. But for most practical purposes, I'm just going to get some chemical reaction that causes electrons to move the way that they don't really want to go. So I'm the pump right here. I'm the battery. I'm the battery in this analogy, and the high voltage to low voltage, I guess this is just a wire, but here this is a resistor because the water slows down after it turns the wheel, right? That's the way that it goes from high voltage to low voltage. And then when it's down here, this is the other side of the wire that leads back to the battery. Okay, so I want you to think of voltage as electric pressure. It's how much the charges are being pushed. All right, very good. Let's leave it there. Potential energy there, and this is a high potential energy, and this is a low potential energy. But you know, really we're not talking about potential energy so much, we're talking more about potential. And so we can start to think about voltage, and it's voltage that determines whether something will cause charges to move or not. And this would be both sides of a wire. Maybe I could say both sides of a circuit at same voltage. And this would be voltage difference. Water is going to come out the low side because of the action of gravity, so this water will be going that direction. I think there are no surprises there. But it really shows us that, well, we can make a beautiful analogy to electricity. This would be a certain potential energy here and a certain potential. Hi, I want to tell you about, well, electrical current, charges moving, so this is pretty exciting. Whenever I hear the word current, I think of current on a river, and we can make all kinds of analogies to water. So let me just start out by saying a couple stupid things about water. If you have a tube of water and you lift up one side and lift up the other side at the same time, then water won't move. You'll have the same level, and yeah, it's all water in here, but it won't flow. But if you have a tube of water and you lift up one side and the other side is not high, then